Hello, everybody. It's me again, Rich Andre. Today, we're going to be talking about affine spaces, which are sort of like a topic in algebraic geometry, and it is also a part of vector spaces, sort of like a subcategory of vector spaces, which is a topic in linear algebra. So, if you guys know what a vector is, we already know what a vector is, okay? So, a vector, suppose we have V vector. The vector is just basically a magnitude plus direction. So, given that definition, given that definition, we could say that a vector, okay, given a particular vector, it always has these two components together. So now we know what the vector is. Now we recall what a vector is. Now let's talk about scalars, okay? So a scalar, if you imagine a two-dimensional plane wherein we have the horizontal line, the horizontal arrow, let's say it's x, and vertical arrow, which is y. Suppose we have a vector, okay? Suppose we have a vector that goes through the origin point, okay, which is the center. And it goes through there. Now a scalar basically just depicts how much of that vector either scales up, either increases in size, or inverts, in the different direction, or basically just the size, if that vector can get bigger, get smaller in both directions, So that's basically what the scalar is. Now let's talk about the main topic of this video, which is the affine subspaces. Affine spaces. I mean. So if you can see here in this definition, there's an important distinction between vector spaces and affine spaces. The vector spaces has vectors and you can add vectors together. And it says here the affine space has points and you can subtract 2 points to get a vector or take a point and add a vector to get another point. But what you can't do, okay, I just have to give this, okay, give this advice. You can't add 2 points together in an affine space. It just says here you generally cannot add 2 points together in an affine space. You can in vector spaces, I believe, but affine spaces you cannot. So the basic idea here is if you can imagine this, okay? We have a 2D. I don't know if this is 2D or 3D, but yeah, it's 2D. Imagine ordinary 2D coordinate geometry. You have points such as P, then X, Y, 2, 3, and Q equals 5, 7. And this general idea, P equals, let's say you have 2, 3, and the other one's 5, 7. P and Q, 5, 7. Okay. So the basic idea here is if you subtract these two, you find the difference between the two, you will get the displacement. AKA the movement of the vector. Okay? So going from P to Q, let's say you have this. you have 2 points. P, which is 2, 3. Say this is P. Then Q is here. 5, 7. Oh, my bad. That's a bad example. Let me just get rid of that. I can't visualize it yet, but if you if you subtract these 2 points, you can get the displacement from P to Q, or aka the movement that happens in order to get from P to Q. So you if you subtract them, you will get 3 and 4. Okay, and that will be the resulting vector. That will be the resulting vector. So if you have P, we can get the displacement by subtracting Q and P, 2 points. Or you can say P2 minus P1. If you guys watched my vector equations video, this is exactly the same sort of, this is the same, equation or the formula in order to get the vector. But in this case, we have points. So we have xy on both points. So you actually have to subtract 4 numbers or 2 sets of 2 numbers. Okay? So let's do the subtraction. For Q, we have 5 and 7. Minus 2 and 3. 5 minus 2 is 3. 7 minus 3 is 4. So this is going to be the resulting vector. Okay. And the distinction, okay, you have to distinguish affine spaces and vector spaces first. In vector spaces, you can talk about points and direction together. So these two are sort of like interconnected. They're related to each other. Okay? But in affine spaces, you can generally make a separation between these two concepts. So you can talk about points and directions separately. So we'll elaborate on that later. But first, let's talk about this displacement, okay? If you look at the explanation here, okay, in affine spaces, you have points, and you can subtract 2 points to get a vector, or take a point and add a vector to get another point. Okay. So if we derive that explanation and denote it into a formula, to a bunch of formulas, Let's take the first principle for affine spaces first. You take the difference between 2 points. Let's say P2 minus P1. Okay? But let's just use another variable because that is the same thing I used for my other video. So let's just use the variable given to us. Let's say let P equals first set of points Q equals second set of points. Okay. And then we get the formula. Let's denote displacement as d with a vector equals q minus p. You get the displacement of q minus p. But the result of this also happens to be the vector. So we can say v is equal to q minus p. The other principle that it says is that you can take a point and add a vector to get another point. So if you have p here, let's say p, and then you add the vector p plus v vector, you get the result of p 2. Okay. So that just means that when you add a point, a set of points, and a vector, you get another point. Okay? So let's get an example of that. Right here. So you can also take a point and move it by vector. Let's say p plus b vector, for example. Let p equals 2 and 3, and b equals 3 and 4. P plus b equals 5 and 7. And that's essentially what affine spaces are. Okay? You're getting the points in the any plane, okay, in any plane that you desire. Okay, so let's continue this. So in order to get the point, okay, point, we just add the first point that was given and then the vector, okay. So this is a set of points and this is the vector. How do we get the vector? We just minus 2 sets of points. So that's basically it for this part of the spaces. Okay, so we talk about why do we need affine spaces. So it says here, suppose we have points p and q. Vector p to p q tells us how to move from p to q. The vector is a direction and displacement. Okay, but p and q themselves are directions. Now we suppose we translate both points by 10 to 20. You get the same displacement as you did earlier. Okay, here. So the vector didn't change. It's a fundamental idea in affine geometry. So this fundamental idea that we're talking about in affine geometry is that the displacements, let's just denote it as this. Okay. Displacements of a vector okay, they do not change the vector at all. They do not change regardless of the scalar. They're still the same. If you get 2 points Let's say you get 2 points. Let's say P is equal to 2, 3. Q is equal to 4 and 5. And you get the displacement between the two. So that's 4 and 5 minus 2 and 3. This is still going to be the vector, regardless if you add any sort of number towards these 4 points. So let's say in the x values of each set of numbers, you add 10, and in the y value you add 20. So you get this, okay. If you get this and you minus them, you minus both of them, you will still get 2 and 2, which is the same as this. So regardless if the coordinates change, okay, regardless of the coordinate change, the displacement is also going to be the same in the vector. Okay, so that's a fundamental sort of idea in affine spaces in geometry and affine geometry in general. Okay, so it says here, the distinction is probably the most important thing you need to understand. So a vector space contains objects called vectors. You can add them, you can add the vectors, then you can multiply them by a certain quantity or a scalar. Everything is based around a special vector, which is the origin of 0, which is 0 vector. So every vector in vector spaces, okay, just to distinguish them between affine spaces, every vector has an origin in vector spaces. And that origin is this, just the 0 vector. Okay? So if you think about it, they always start at 0. Both in x and y values, they start in 0. Whatever vector in a vector space, but in affine spaces, you can have no such special origin. Okay? So if you see here, let's take this example from ChatGPT. It says here in an affine space, there doesn't have to be a special point to access the origin. So essentially, what it says is that in affine spaces, the distinction between the two in affine spaces, it doesn't matter where the vector is. Okay? It doesn't have to sort of originate or start from 0 and 0. Okay? For it to be a valid vector. In affine spaces, you can have no origin at all, or whatever number it originated from. It's just that there doesn't need to be a special point. As it says here, there doesn't need to be a special point that acts as the origin for the vector. Okay? So this is what I said earlier. If you move your coordinate system somewhere else, the coordinates of P and Q might change, but the displacement between them remains the same. The same idea here. So there are the 3 fundamental operations. Okay, you can just affine space essentially allows 3 important things. If you minus 2, if you get the difference between 2 locations or 2 points, you get a vector. Okay, and if you add, okay, if you get the sum of a set of points and or location in a certain space, you have to add it with the vector. If you add it with a vector, you still get the point. You still get another point. So this is just the sum of these two. It's just another point in the surface or the plane that we're using, or whatever plane you're using. So the third fundamental operation is that vector plus vector is equal to vector. If you add two vectors, you get another vector, or the sum of those two vectors. But what you can't do, as I said earlier, is extremely important. You can't get the sum of two set of points. Because it says here, y. You get the y of it, because two locations don't naturally combine to produce another location. That makes sense, you know? Because if you're thinking about it, try to visualize it. Let's say you have this plane. Say you have 2 points. You have 1, 1, and 1. And then you get another point, which is -1 and -1. If you add these two, together, you get 0 and 0. And where is 0 at? Here. And it says here, two locations that naturally combine to produce another location. And it doesn't produce another location, right? It just goes to a location that is already there. Doesn't go to another location. If that makes any sense. Okay. If we could take this example as well. For example, saying 2 and 3 plus 5 is 7. Or 7 and 10. It says it's something we can naturally calculate numerically, but geometrically, this isn't an intrinsic operation of points. The results depend on your chosen coordinate system. Okay? So there isn't an intrinsic operation of points. So now we can think about the useful meta models that we can use to think about affine spaces. You know? Before that, let me just P, Q, R. These are locations. Whatever variable you can see like this, these are locations. And vectors, okay, vectors have these arrows on them. And they basically just describe movement. So if you can see here, location plus movement equals location. Just like P plus Q, just like P plus V equals P2. As I said earlier, location minus location is displacement. That's the movement. That's a good mental model to really understand what happens here. Okay, so we have to talk about affine combinations. So it says here, this is one of the most important mathematical concepts in affine spaces. Suppose we have points P1, P2 in ... and Pn. An affine combination is an expression like A1, P1 plus A2, P2 plus A1, A and Pn, where the coefficients satisfy A1, A2 plus An equals 1. So they must always equal 1. The coefficients that are inside. Okay, let's say you have a point. Let's say you have this point. Let's say 1, 2, and then 3, 4 for point 2. Now the points here should equal the coefficients of the points should equal to 1. So for example, if we have here -1 and then we have here +1, Okay. No. If you have a negative 1, we have positive 2 here. Negative 1 plus positive 2 is going to be 1. So the coefficient will be equal to 1. Let's see another example right here. Now, if we have a coefficient for the points P and Q of 1 half, 1 half plus 1 half, that's 1. So that's correct. And if you add both of those, you're going to get the midpoint of P and Q, which is kind of like the median of the P and Q of both sets of points or locations. Okay, so that's affine combinations. If you think about it, affine combinations are sort of like Feynman. How do you call it? Fibonacci sequences. They're sort of like Fibonacci sequences, except that the coefficients is equal to 1. Coefficients should equal to 1, and there doesn't need to be substituting. Okay. And affine combinations basically just describe points on lines. Therefore, the line is xy. So if you have a affine combination like this, the coefficients should equal to 1. Then if you add them, you distribute them. Okay, this should be the answer. Okay, this should be the line, which is the exactly the usual parametric equation of the line. Okay, so we can do that. Let's say so we just have to distribute and substitute. 1 times 1, that's positive 1. Negative 2 times negative 2. Negative t times negative 2. Negative t times positive 2, I mean. Yeah, negative 2t. Okay, check. We actually have to FOIL, I believe. Sorry about that. So we have to FOIL that. We have 1 and 2 here. First, 1 times 1 is 1. Is that right? So there must be a little mishap here. Let me just check. 1 negative t and 1. Wait, maybe wrong on this. Let me just get the actual answer here. Scale 1 minus t, 1, 2. Let's just try to derive the answer from the actual, you know, the actual answer. Let's try to find out what happened here. 2t. So we have here plus 5t, 6t. All right. So I'm assuming what happened here is that. Okay. See, we have another t here. So another t times. Oh. Okay, let me just distribute two binomials. Yes, we have formatted. I was right. Maybe I was wrong. I don't know. I don't really know how they ordered this, but we can just skip the orders. But I believe they foiled this. So if you have that, now you have to add these two. So what happens here is I don't know what happened here. I don't really know. Maybe they distributed it, something. Because this here's 2 plus 4. The second pair turned to 2 and 4. Mhm. I don't really know. It just turns out to be this way. Let's just skip that. So this is obviously displacement, okay? So if you search up vector subspace, yeah, so you can just definitely think about subspaces as subsets of a certain set of points, where certain points extract from a certain set of points that has these rules, okay? These three rules right here, which says non-emptiness, the zero vector is in V, closure under addition, okay? The zero vector is in V, okay? Closure under addition, if U and V are in V, then U plus V is also in V. So for translating that, okay, affine subspaces are just sets or subsets of a set. So for example, we have a set of 1, 2, 3, 4, and we have a subset of, let's say, U is equal to 1, 2. Then U is a subspace of this, provided that U, okay, let's say you have 2 points. Let's say you have 2 points. Let me just so let's say you have these 2 points. It says here that these three rules should apply. So these are obviously subsets of this uh, uh, general set, but the zero vector should be in V. If U and V are in V, okay, if they both in V, this is V. If U and V, then U plus V is also in V. They should, if you add both of those, you get 4, 6. These two numbers should also be in here. In order for them to be a subspace. Lastly, closure under scalar multiplication. If V, okay, V is in V and C is in R, let's say we have a C. Say we have 1 times 2. So we have an external variable. We have a third variable here to consider for a subset to be a subspace of for something to be an affine subspace. These three rules should be met. Okay. So if C is 1 and 2, if you multiply V and C, you should get 3. 4 times 2 is 8. You should get the numbers here as well. They should also be in the general set for them to be a subspace. That's basically what affine subspaces are. Basically just subsets of a certain set of points or locations that meet 3 criteria, which are these, okay? So let's go and so we're just going to leave it off in affine subspaces, but we're going to continue this in another time. Thank you guys for watching. I'll see you guys in another video. Peace.